This is Salisbury Fire Department's Training Minutes.
David Haynes, training captain for the Salisbury Fire Department. We're continuing on with our hydraulic series of training minutes, and we're talking about relay operations, and we're calculating the pump discharge pressure for an engine in a relay using the formula above here. As you can see, the formula is set up for relay operations. The first element, instead of being a nozzle pressure as it would be for an attack engine, we have RP in there for residual pressure. And just as a refresher, this is a memory jogger. So you always want to account for all of those elements. That includes your nozzle or residual pressure, your friction loss, your any devices, or any head pressure or elevation loss or gain that you would have in determining your pump discharge pressure. So as you can see over here, I have 0 already filled in because we have no devices and no elevation changes to worry about. So I've gone ahead and accounted for those. Again, go ahead and account for them, that way you always remember to. So that leaves us with the friction loss and the residual pressure that we're going to figure out to get our pump discharge pressure. So starting with the residual pressure, that's a fairly easy one. We know that we're going from pump to pump in a relay. Always want to try to give the driver operator at the other end of that relay a little bit of working pressure on top of what they're flowing. So what we try to do is always give them 50 pounds to work with. So we'll go ahead and plug that into our equation here. 50 pounds residual pressure pump to pump in a relay operation. So that leaves us with the friction loss. And we're working with the Ham method, the Q-squared method, and then we're using conversion factors. The Q-squared baseline always gives us a 3-inch hose number. That's the 3-inch friction loss in a 100-foot section of hose. And then to go from 3-inch hose to another hose size, either you convert by either multiplying or dividing. If you go from 3-inch hose to 2.5, which we did in our previous training minute, we had the conversion factor of times 2. So Q squared times 2 for 2.5-inch hose. We also did conversion from 3-inch hose to 4-inch hose. And if you go from 3-inch to a smaller hose, the friction loss is going to increase, so we had to multiply. If you go from 3-inch hose to a larger hose, the friction loss will decrease, so you end up dividing. So the conversion factors for the larger hose, 4-inch, 5-inch, and 6-inch hose. We did 4-inch hose in a previous training minute, and that was a conversion factor of dividing this number by 5. And today we're dealing with 5-inch hose. That conversion factor to get from 3-inch hose to 5-inch hose is to divide by 15. And we'll go ahead and plug that in here. So Q squared divided by 15 will give me 5-inch hose. If we were dealing with 6-inch hose, even larger hose, the friction loss drops significantly, and that conversion factor would be divided by 30. We're not going to go into that today, but if your department uses 6-inch hose, just be aware that the conversion factor from 3-inch to 6-inch, that's the number, divided by 30. So 15 for 5-inch hose. Our chart's already set up here for what we were working with before. We're going to plug in a gallon per minute number, a length of hose. We're going to calculate the friction loss, and as always, we're going to account for the flow, the size, and the length. So the size, we always start with that baseline of 3-inch. We're going to convert to 5-inch divided by 15. So that's the final number per 100 foot that we'll come up with. So I'll go ahead and plug that in over here so we know. 5-inch hose, conversion factors divided by 15. So, quick refresher on the Ham method. Today we're dealing with larger hose, so we're going to be dealing with 600 to 1,000 gallons a minute. 600, 700, 800, 900, or 1,000 on our Ham method. Gallon per minute flow per finger. And then the base of your palm down here, your memory jogger, is a multiplication symbol down there. So that's the 3-inch hose method. So we'll come up with a gallon per minute flow here. We'll say 1,000 gallons a minute. We'll go big or go home. 1,000 GPM. And then we'll say it's 1,000 feet of 5-inch hose. So flow size and length, we'll start with the flow. We'll plug 1,000 right up here. 1,000 gallons a minute. The very first step when we do our Ham method is to take the flow, divide that by 100. So essentially you're going to knock off the last two zeros. So 1,000 divided by 100 will give us 10. And that is on our hand method here. 600, 700, 800, 900, 1,000, 10. Our memory jogger at the bottom with the multiplication sign for the q squared. So 10 times 10, that would give me 100. So the squaring method would tell me that for a 3-inch hose, every 100 feet, flowing 1,000 gallons a minute, there's about 100 pounds of friction loss. Okay? We're going to move from 3-inch hose to 5-inch hose, and we're going to take that number and divide that by 15 to convert it. So if I take 1,000 gallons a minute, end up with 100 pounds per section at 3-inch, and I convert that by dividing by 15, I'm going to end up with roughly 7 pounds of friction loss. Again, this is fire ground hydraulics. Easy math at 2 o'clock in the morning, it's going to be close. But with minimal friction loss like that, if you were to say 7 or 8, you'd be right on the money. So 7 pounds is what we'll say per 100 foot of 5-inch, flowing 1,000 gallons a minute. So we've accounted for the flow. We've accounted for the size of the hose. We used the hand method, started with 3-inch, converted to 5-inch hose, and now we're going to deal with the length. So we have 1,000 feet of 5-inch hose. We'll plug in 1,000 over here. And then we do the same thing we did here. We divide by 100, or essentially knock off those last two zeros, like we did up here, and we'll end up with 10 again. So to get to our friction loss, we know we have 7 pounds per 100 foot, and we have 10 100-foot sections. So we multiply the number here times the friction loss, and that will give us 7. So in this relay from engine 1 to engine 2, we have 1,000 feet of 5-inch hose flowing 1,000 gallons a minute with 7 pounds of friction loss per 100-foot section for a total friction loss of 70 pounds. Plug that into our formula up here and add those elements together. 0 for your head pressure, 0 for your devices. Always get in the habit of accounting for them to make sure that you remember to account for them. Friction loss of 70 pounds and the residual pressure at the end at the other pump of 50 pounds. So we put those two together and we should have 120 pounds of pump discharge pressure for this example. So what we'll do now, we'll repeat this and we'll do it with an in-between number and then come up with a different number. So knowing that we're going to keep things roughly the same, we'll take away this because that's going to change. We're going to keep the residual pressure. We know the friction loss will change. We're not going to add devices or head pressure. We'll leave that alone. So 0 and 0 for them. And then we'll take the rest of the numbers out. So, an in-between number. If I have a whole number, 600, 800, 1,000 gallons a minute, that's an even multiplication. And our hand method is a multiplication sign in the palm. You go to that corresponding finger and square that number. So 8 times 8 or 10 times 10. If I have an in-between number, such as 750 gallons a minute, 850, 950, I come across, and instead of just dividing by 100, we cross multiply. So we'll put a little note right here, we cross multiply, and then we'll say for this example that we're flowing 850 gallons per minute. And then we'll come up with a hose length, we'll say 900 feet of 5-inch hose. Again, the examples doesn't matter, just you're working with numbers here. So the first thing we address, flow, size, and length. Go to our flow, we have 850 gallons a minute. So 850. We know that because that's an in-between number, we're not going to be able to simply square that. So we cross multiply instead. So come across, use our hand method. 600, 700, 800, 850 falls between 800 and 900 gallons a minute. So we cross multiply 8 times 9. So 8 times 9, we're going to come over here, and that should give us 72. And that is the friction loss for 100 feet of 3-inch hose flowing 850 gallons a minute. So To go from 3-inch hose to 5-inch hose, we're going to divide that number by 15. So 72 divided by 15 is about 4 and change, so we're going to say 5. So for every 100 feet of 5-inch hose flowing 850 gallons a minute, there's approximately 5 pounds of friction loss in each section. So we've addressed the flow, we've addressed and converted for the size of hose from 3-inch to 5-inch using our hand method. Now we're going to address the length. So we have 900 feet. We're going to come over here, divide that by 100, or essentially knock off those zeros. That tells me 9. So 9 100-foot sections, 5 pounds of friction loss per section. Multiply those two together, and we end up with 45 pounds of friction loss. We plug that in up here, and our final pump discharge pressure, we're going to add all this together. No head pressure, no elevation, no devices, 45 pounds of friction loss, and 50 pounds residual pressure at the end of our relay going pump to pump. So total pump discharge pressure on that 5-inch line of 95 pounds. So that's been a review of the pump discharge pressure calculations for 5-inch hose in a relay operation. That's today's training minute. Thank you.